What we want to go over in this set of lectures are inductors and capacitors. These are two new linear circuit elements that we'll discuss, and we'll continue to include them in our lectures and discussions and problems throughout the remainder of the semester. So we'll look at the capacitor in this lecture, and then we'll look at the inductor in the next lecture. These elements are different from resistors in that they don't dissipate energy. So in other words, what a resistor really does is it takes electric power and it converts it to heat. In the capacitor and the inductor, for the ideal elements, they're not going to do that. They're going to store the energy. So the bullet point says they instead store energy, but you need to be aware that in a circuit, capacitors and inductors are capable of storing and releasing energy. So that's part of how they function. So what we're going to do in this chapter, which is chapter 6, I believe, of your textbook, we're going to look at just the capacitors and inductors initially and some of the physics behind them. And then what we'll look at is how they behave in circuits. So we'll start with the capacitor. And let me get a screen view. We'll start with the capacitor. The best way to visualize a capacitor, and they don't all have this shape, but the best way to visualize it is that you have two metal plates. Each plate has an area A. They're separated by an insulator that has by a separation distance D. And all insulators are characterized by the permittivity, the dielectric permittivity. And so this insulator in the capacitor has some dielectric permittivity. That's just a constant called epsilon. Typically, plates are aluminum foil. The dielectric can be air. It can be a ceramic. It can be paper, plastic, or mica. There is such a thing as a capacitive microphone, where one of the capacitive plates is specifically built where it'll move in and out, changing the capacitance of the circuit. So they're not necessarily always applied the way they appear here. I can also say that, let's go to the next page, because I believe the formula for capacitance, the formula for the relationship between the charge stored in a capacitor and the voltage is that Q is equal to CV. And what I want to get to is the formula for capacitance. So here's the formula for capacitance, and you notice that it's proportional to the area of the plates, and it is inversely proportional to the distance between them. So what I wanted to do was talk a little bit about this. A lot of times when you buy a capacitor, if it's what we call a high energy density capacitor, in other words, it's built to store a lot of energy, it comes in like a can. And it has two terminals at the top for its connections. So what usually is inside here is they take this geometry, and in order to make the area larger, they'll literally roll it up. So if you were to cut the top of this can off and look inside from the top, you'd see this guy coiled up in a coil. So they mostly preserve the spacing between the two aluminum foil layers. They use a bendable dielectric like a paper. Oftentimes it's a paper that's been saturated with oil that increases the dielectric constant and makes it less likely that it'll be damaged. And then they roll it up so that within this sealed containment you can get a larger area. So that's a common technique in building capacitors, where you want to store more energy than what you could get from this simple parallel plate geometry. So when a voltage source is connected to the capacitor, basically what happens is a charge accumulates on the plates. So you'll get a positive charge that distributes on one plate and a negative charge that distributes on the other plate. So they're equal and opposite. So they're equal in magnitude but opposite in charge. And the amount of charge that's deposited on the plates is proportional to the voltage. So Q, the charge, is equal to CV. C is the capacitance. And then we saw for a parallel plate capacitor that the formula for the capacitance is epsilon A over D, where A is the area of the plates, D is the distance between them, and epsilon is a constant dependent on the dielectric that's placed between them. One of the common or one of the current areas of research, particularly in integrated circuits where you build capacitors on a chip, is to look for dielectrics that have permittivities that can be designed, because you are on a chip somewhat limited in both area and separation distance. So really the only parameter that you have to play with is the permittivity. Okay, the unit of capacitance is the farad. 1 farad is 1 coulomb per volt. Most capacitors would be somewhere in the range from a picofarad to a microfarad. Very uncommon to have a capacitance of 1 farad. So you're usually, when we work some problems this semester with capacitances, you may see some units of farads or millifarads, but that's just for ease of calculation, so that you're not having to enter 10 to the minus 12 and 10 to the minus 6 and 10 to the minus 9. So just so that you know that. So capacitance is determined by the geometry. The parallel plate capacitor is not the only kind of capacitance you can have. You can actually have a coaxial capacitor. In that case, this formula would not apply. This formula comes from electromagnetic fields. If you've had physics 2, you may have calculated this one. It comes from electromagnetic fields. Using Gauss's law, you can calculate a ratio between voltage and charge, and that is indeed the capacitance. You can do the same for a coaxial or even a spherical capacitor, but you won't get this formula. So types of capacitors, most of them are what we call film capacitors, and here's what I was saying earlier, that they're often rolled up before they're housed in a container. So they're made of metal or plastic films, and then they're rolled up. Electrolytic capacitors produce a very high capacitance. Trimmer capacitors have a range of values that you can set them to. So in other words, they're variable. And then variable error capacitors can be adjusted by literally being able to move the plates. So I talked a little bit about the capacitive microphone. That's how that works. It picks up basically the sound waves. The pressure from the sound waves will vibrate one of the capacitive plates, hence changing the capacitance and then giving you a variable voltage. Now, this Q equals CV formula is an important formula, because that's how you derive the formula for capacitance. That comes from physics. As I said, it comes from Gauss's law. However, what we really would like is a relationship between the current and voltage in the capacitor. So let me see if I can't. And you do that by taking the first derivative of that equation, Q equals CV. So this came from Q equals CV. We took the derivative of both sides. On the left side, we had dQ dt, which is equal to the current. On the right side, we had C dV dt, and we are making the assumption here that the capacitance is a constant. So the little discussion of variable capacitors and changing capacitance in a circuit, that's going to change the way you analyze things. So for now, for this class, we're assuming that the geometry of the capacitor and the dielectric constant are fixed, and so hence we have this relationship where C is a constant. Let's go back. Oh, and by the way, this is assuming the passive sign convention. So what is the passive sign convention? The passive sign convention is that current flows into the positive voltage terminal. So when you write that equation for the voltage across a capacitor, you're assuming current in this direction and voltage in this direction, plus to minus. Some additional applications. Capacitors can be used to block DC voltages. They can similarly be used to pass AC voltages. They can be used to shift the phase of a voltage, which we'll talk about a little bit when we get to AC. They're used to store energy. They can be used to suppress noise, and by that I mean electrical noise. So a capacitor can be used in a certain configuration to reduce noise. Start motors is kind of an interesting one. Oftentimes, to start a motor requires significantly more current than to operate the motor. And so, what you'll often do is have a capacitor that is available to provide some kind of boosting current to the system so that you don't have to have your whole electrical system such that you can provide that level of current. So, the capacitor is there to provide kind of a boost current for what it's worth. I want to go back to the formula for the current compared to the voltage, and I want you to notice a couple of things. First of all, if the voltage is a constant, so if the voltage is DC, the derivative of a constant is equal to 0. So what that means is no current flows in the capacitor under DC conditions. Now, what else occurs in circuits where no current flows? Hopefully you're thinking the open circuit. So in a DC system, capacitors look like open circuits if the voltages are all constant. It's only when voltages begin changing in time that we get a current in that capacitor. Also notice that the faster the voltage change, in other words, if we had a plot of like various changes in voltage. So this would be our V and this would be time. So if we had a plot like this, obviously this curve where the voltage changes more rapidly has a higher slope. So what the current is really equal to is it's equal to the slope of the change of the voltage with respect to time. So if voltage is changing very rapidly with respect to time, we're going to get a much bigger current. Now, what happens when you try to make the voltage change instantaneously? So let's suppose we have this voltage, it's a constant, and then suddenly we want to reset it to a higher number. So we have this little step here where the voltage changed instantaneously from value number 1 to value number 2. What would happen there? Well, this is a vertical line, and hopefully you remember from Cal 1 that the slope of a vertical line is infinity. So if we try to change the voltage across a capacitor instantaneously, it's going to try and draw infinite current. So physically that can't happen. So the voltage cannot change instantaneously across a capacitor, and a capacitor looks like an open circuit under DC conditions. Those are two separate but equally important things to remember about capacitors. Now, if we want to find the voltage across a capacitor in terms of the current, we can take that equation, I is equal to C dV dt, and we can integrate both sides. And when we do that, we'll get the voltage in terms of the current, where we start at some, because it's an integral, so we have to define limits, or else we'll have a constant of integration. And if we want to know an actual voltage, we don't want an undefined constant. So if you integrate the left side from V at some t sub 0, some starting point, to V of t, an arbitrary time, you'll get over here V of t minus V of t 0. And then over here, you'll get the integral of the current. So when you move the V of t0, which is the initial condition, over here, this is what your equation looks like. So once again, let's talk about each part of this equation. So let me erase real quick, and let me go back. So let's talk about each part of this equation. This part, V of t, well, let's try this again. V of t is the voltage as a function of time across the capacitor. They just use tau here because they want to have a variable to integrate across, and they don't want to use time. When I work with this in notes of class, I just use t everywhere because I'm not so mathematically strict. we have 1 over C times the integral of I of t dt, where I is the current. And then we have to have, in order to find the voltage, we have to have knowledge of the initial condition. In other words, what voltage was on that capacitor when we started measuring the current. So this shows that the capacitor has kind of a memory. So the capacitor voltage is dependent not only upon the current at this instant, it's also dependent on what its voltage was at a previous time. So you can imagine that this might be useful in some circuits to have something that is dependent not only on the current state, but also on a previous state. The instantaneous power can be found by taking V times I, where we substitute C dV dt for I. And so this is the formula you get for power. That's usually less interesting to us than the energy that's stored in a capacitor. So as you know, energy in general is the integral of power. If we assume we start with 0 energy and we integrate this equation, then we get the following formula for energy that tells you at a given voltage, V, how much energy is being stored in that capacitor. So the energy is 1/2 CV squared. Okay, so in circuits, we're going to start with an ideal capacitor. What the ideal capacitor means is that the elements in the capacitor are perfect. So the metal is a perfect conductor and the dielectric is a perfect insulator. So that's going to mean 2 things. First of all, it's going to mean when the capacitor is under DC conditions, there's no current that flows through the capacitor. So if the voltage isn't changing, basically the voltage sits there on the capacitor, the current is 0, nothing leaks, etc. So the other thing is the voltage on the capacitor plates can't change instantaneously. An abrupt change in voltage requires an infinite current. So if the voltage on the capacitor is not equal to the voltage that you apply, then basically charge is going to move until the voltage on the capacitor reaches the voltage that you apply. So we call this charging a capacitor. You typically will charge a capacitor using a resistor for this reason. So if you want to put 10 volts on a capacitor, you would take a 10 volt voltage source. You would almost always use a resistor to limit the current and let that capacitor charge. So that's just kind of a practical aspect of capacitors. An ideal capacitor will not dissipate any energy, so that means that your capacitor plate is a perfect conductor. It doesn't have any resistance associated with it. So a real capacitor will have a parallel model leakage resistance, meaning an actual capacitor has a little resistor in parallel with the capacitor, and that represents the fact that no insulator is perfect, and so it will leak a little bit. In order to model a small amount of leakage, we need a very large resistor because not much current is going to leak there. Some people will also model the finite conductivity of the plates by placing a little resistor in series with the capacitor as well. So when you actually model these things, they have some additional components that show up. Okay, so without going in great detail about resistors in series and resistors in parallel, you can demonstrate by using KCL that if you have a number of parallel capacitors, that the rule for combining those is actually the opposite from combining resistors. So let me skip ahead here. This is what happens when you substitute the relationship for each capacitor and its voltage into that KCL equation. And so you can do a little mathematics and find that when you have a bunch of capacitors in parallel, you get an equivalent capacitance that's equal to the sum of the parallel capacitors. So parallel capacitors will combine as the sum of all of the capacitors. It is the opposite of the rule in resistors, because we'll also see that series capacitors, if we were to write a KVL equation and try and get an equivalent capacitance there, capacitors in series are going to combine as inverses. So you can look through this little derivation. This is the voltage across each individual capacitor in series. If we then combine all of those initial condition voltages into one, because they're all in series, so they can all be added, and then we gather like terms on the current, we find that there is an equivalent capacitance. 1 over the equivalent capacitance is equal to 1 over the sum of the individual capacitors. So series combination of capacitors is the same as parallel combination of resistors. So another way to think about combining capacitors is the following. If you think about combining capacitors in parallel, you can visualize a bunch of those capacitors in parallel, and that actually is increasing the surface area of the capacitors. Since capacitance is epsilon A over D, a bigger A would give you a bigger capacitance. A series combination, if you put a bunch of capacitors in series, you can sort of visualize this as analogous to increasing the total plate separation D, and that would result in a decrease in capacitance. Whether that helps you remember, I don't know. Maybe it will. There's probably better ways to look at that from a voltage current point of view, but this is kind of a nice little visual reminder. All right, we're going to stop the video here, and we'll take up on the next video with inductors.